Hello, everyone, and welcome back to the afternoon session of today's Attochem workshop. If some of you might have already realized, I'm not Stephanie Gräfe. My name is Karl-Michael Thiens, and I'm working in the group of Stephanie Gräfe, and I'm substituting as chair this afternoon for her. We have four interesting talks lined up, and I'm very much looking forward to interesting and stimulating discussions. I just want to mention two things very quickly. Number one, if anyone wants to ask a question after one talk, please raise your hand using the Zoom application. And second, after the four talks at 3:40, there is the opportunity for Meet the Speaker. Please just look at the Attochem WG2 website. There you can find the corresponding links and use the password provided via mail to all participants. Okay, let's get started with our first talk, which is by Aurélien Delalande from the Institut de Chimie Physique in Paris, France. Incredibly sorry if I mispronounce anything here. Please feel free to correct it. And they will talk about the promises of auxiliary DFT to investigate radiation chemistry problems. So please go ahead, Aurélien, the stage is yours.
Yes, thanks a lot. Sorry, I had a problem with my Zoom on Linux and Windows, so it was a little bit problematic. Normally, I think it should be okay now. I will share my screen. Up. Oops. Is it okay now? Can you see the screen?
Yes, we can see it. Maybe you can go into full screen mode or presentation mode.
Yeah, how do you see it? For me, it is a full screen.
For us, we can still see the slides on the left side. And maybe you can go to presentation mode if you go to view.
Sure.
In your PDF settings.
It's a PDF.
Yeah, go. Let me have a look myself. If you go to.
Is it better now?
Full screen mode. Yes, perfect. That's perfect.
Okay. Okay. I think I lost the animations, but it's not a problem. Okay. So shall I start? If
yes.
It's okay for everybody. Okay. So, well, hello everybody. I would like first to thank you, all of you, to be here, and also to the organizers of this meeting from the Cost Action. So I'm really happy. It's my first participation, so I'm really eager to have scientific exchanges with all of you. So what I would like to talk about today is the use of auxiliary DFT to investigate radiation chemistry problem. So we are in a lab in University Paris-Saclay in the south of Paris, and we are essentially physical chemists, and we are interested in radiation chemistry. So maybe I should just introduce a little bit for the audience what I mean by radiation chemistry and what are the types of problems in which we are interested. So we are interested in the consequences of the interaction between high energy particles like X-ray or gamma rays, or like charged particle like kilo electron volt, mega electron volt proton, helium, and nuclei, when they interact with biological matter. So it is a known problem for a long time in medicine and biology, because it is known that such particle can induce chemical damages on DNA, proteins, lipid that lead to aging, cancers. And so it is important to understand how they interact. It's also, on the other hand, a promising tool for radiotherapies, and to use, for example, protons to cure certain cancers. But this type of interactions are also involved in chemistry, for example, for X-ray imaging of biomolecules. in astrochemistry, where cosmic rays are probably key players in the chemistry taking place in the interstellar medium. And for example, if we wonder about the formation of prebiotic chemistry and prebiotic molecules. This is also an issue, these ionizing radiations in aerospace industry. So when we send electronic devices or human being beyond the Earth's magnetosphere, this ionizing radiation can also have important consequences. And finally, of course, we can think about nuclear chemistry, where, for example, helium nuclei are produced in the reactors and can damage, for example, the reactors or the effluents in the output of the nuclear plants. So this is a general context. In our lab, we are essentially interested in the case of biological irradiation and essentially DNA and proteins. So I usually like to start this kind of presentation by making a strong difference between photochemistry and radiochemistry. We also already heard a little bit about such differences this morning with one of the talks. In photochemistry, we are usually dealing with low energy excitations, quite localized on some molecules, whereas in the case of radiation chemistry, the amount of energy which is deposited within the biological structures is much higher, typically tens of electron volts per molecules. The energy is widely spread throughout the molecule. I take the example you can see on the left. It is what is called a nucleosome. So in fact, it is the basic unit constituting the chromatin in our cells, and you see a double DNA strand which is wrapped around a core of proteins. And in this case, it's really schematic, but I illustrate the irradiation by a nuclei that would deposit a lot of energy in the red zone and induce a lot of chemical damages throughout the trajectory. And of course, because we are dealing with ionizing radiations, a really huge amount of secondary electrons, that's how they are called, are produced along the track, and they further irradiate the biological matter. So the situation is much more complex than in photochemistry. Already photochemistry is complex, but it is also extremely complex here. So of course, the fact that such ionizing radiations are induced damages on biomolecules has been known for a long time, and well, researchers have been working on that for decades. But there are still parts of the scenario which is I would say black. This is a representation, a 2D representation of the consequences of the irradiation of biological matter by ionizing rays. So I'm sorry, I don't have any animation now. It's a PDF, so it's a little bit messy. But let's for example, just look at the time arrow. You would start at the attosecond time scale by the irradiation itself that will induce an electron dynamics within the system. A lot of energy is deposited, and this will eventually leak into the nuclear modes. And so rapidly on the femto picosecond time scale, you will have a coupled electron and nuclear dynamics. I think this is familiar for all of you, which will later lead to the production of a lot of reactive species that will induce chemical reactions on DNA proteins that will in turn induce to local deformation or rearrangement of the biological structures that will on longer time damage and make the biological machineries less efficient or worse, in fact. So for a long time, in fact, in radiation chemistry, I would say the picosecond to millisecond time scale was mainly the time scale of investigation. And this was because the time resolution of pulse radiolysis experiment is limited to the picosecond time scale. So basically, we don't really have information with such experimental setup below the picosecond time scale. So there are still many things to understand on longer times, but where we are trying to work is on the lower time scale, from the attosecond to the picosecond time scale. And here, in fact, really few is known about the mechanism of ionization, deposition of energy, the relaxation on the early time, and the formation of the very first chemical damages. And this is where we are trying to work. So our objective, I would say for long-term objectives, are the following. We would like to understand, what we call the direct effect, which is all the chemical consequences of deposition of energy within the biological structures, and how it takes place, on how energy is deposited, relaxed, and what are the first mechanisms that lead to chemical damages. So this is a general context. Obviously, we need to work from the attosecond time scale, where to describe the deposition of energy. And what we would like to do is to do that by first principle approaches. We would like then to meet the sub-picosecond time scale to really account for the ultra-fast chemical reactivity, and that's the hope, long-term hope, to be able then to reach a picosecond time scale and to bridge to the longer term consequences. So this is, again, the nucleosome that I represent. And one of the hallmarks of radiation chemistry is that you really need to deal with large molecular systems. We cannot just consider a few molecules with a few atoms, because the physics of such kind of interactions involve a lot of molecular fragments, the emission of electrons. And so what we have been trying to do in the last years was to start developing dedicated simulation tools for this type of applications. So for the moment, we are essentially on the first stage, very attosecond to femtosecond time scale, and that's what I will show you from now. So the outline of the presentation will be the following. I will introduce you the auxiliary DFT framework on which we are working, how we couple it to a polarizable force field to be able to tackle biological systems. And I will, depending on the time, show you a few examples of applications of our tools to radiation chemistry problems. So we are, for the moment, focusing on the deposition of energy by high energy particles, and we focus for the moment, because it is the simplest for us, on mass particles that we consider as classical particles. I think it's a good approximation when we consider proton in the range of the mega electron volt or helium nuclei. So this is a scheme showing you what is the kind of physics we wish to describe. It is elastic and inelastic collisions of such particles with the electron cloud of biological molecules, which will produce electronic excitations, eventually emission of electrons that we call secondary electrons. And what we would like to investigate are the subsequent energy relaxation and dissipation mechanisms, and also eventually all the charge migrations that could take place within biological systems. So we started from something which is well known in the literature, of course, that you all know, is time-dependent density functional theory. So we consider the Concham framework. Here I give you the well-known range and growth Concham time-dependent equations for the Concham orbitals that involve the Concham potential, Vt, with essentially three components here: the electron-electron repulsion, the exchange correlation potential. Just as a remark, for the moment, we only consider simulations in the context of the adiabatic approximation. So we ignore completely, for the moment, explicit time dependence of the potential. And we have finally the external potential that involve both the potential created by the nuclei of the molecules and, of course, the potential created by the projectile that will irradiate the system. So we wish to carry explicit propagations. So we have coded, in fact, Xiaoqing Wu has coded all these equations in the software Daemon2K, which is a DFT code based on Gaussian type orbitals. So we use, this is not new at all, just to summarize, well-known in the literature. We use a standard, if I can say, or well-known and well-established propagation algorithms. We have tested various algorithms. Finally, the one we use is a second-order Magnus operator, which is equivalent to the split operator. So we work essentially, we propagate, in fact, the electronic density matrix, and not directly the Concham orbitals, but just for the information. So this is the propagator that we need to evaluate, that involve an exponential of the Hamiltonian matrix. This is this propagation is done either with, again, I go fast because I think this is well known. We use either an iterative or a predictor-corrector schemes to propagate the electronic density matrix in time at fixed position of the nuclei for the moment. So I can give you details on all of this, but I think this is really not new. We are just working from what is known. And this is what we are doing for the exponential of the matrix. So we implemented this with expansions, essentially Taylor or Chebyshev expansions using the Scalapack libraries. So where we I think started to put new things into the framework is on the use of auxiliary DFT. So to get the potentials that we need to do the propagation, we start from the definition of the electronic energy. So this is all written in matrix notations. So where you have the core contribution, so kinetic energy of the electrons and interactions with atom nuclei. The second term is the electron-electron repulsion that involve the four centers integral, the exchange correlation potential, and finally the interaction with the external projectile. So first thing is to avoid this four centers integral by the use of variationally fitted densities, rho tilde, that you have here, that are expanded over monoatomic centers that allow to avoid completely the use of four centers integral. This is what you have in the third lines. Now you have only three centers electron repulsion integrals. And the other thing is that we use these fitted densities also to evaluate the exchange correlation potential. So to get the potential, we get the derivative of the energy with respect to the density. And this is the last line. And as you can see, the potential, the Concham potential, doesn't depend anymore on the Concham orbitals. They only depend on the fitted densities. So this is why this framework is called auxiliary DFT by Andreas Koster, who developed this framework. And so what we tried to do was to see if this framework developed for stationary DFT calculation was also suited for real-time propagation. The use of fitted density for us as another use is to analyze the electron dynamics that is evolving in time in our case. We wish to evaluate, for example, and investigate a charge migration process. So we have to carry out repetitive calculation of atomic charges, typically every 5 or 10 attoseconds. And so for large molecular systems, it can be a quite expensive task. So we showed that we can also perform population analysis, provided some care is made on the fitted density instead of the density. So this is an example. You have two diagrams showing on large benchmarks the error that was made using rho tilde instead of rho to extract population atomic charges, or for example, atomic intrinsic dipoles. So this is a rather safe use of the fitted density also for this type of analysis. So we validated the auxiliary DFT framework for real-time with various examples. So this is just one where we evaluated the solvatochromic shift for the absorption of this dye. So this was I will come back on this later, a QMMM calculation. So you have on the left the electronic electronic spectra calculated with standard linear response TD-DFT calculation or with real-time TD-DFT calculation. So you see that you have to compare by color. This is this is rather safe to use auxiliary DFT. So we have made other tests. This is safe as soon as we take care that the auxiliary basis set that we use to expand the fitted density is flexible enough. So the advantage of auxiliary DFT is, of course, the computational performances. So we are currently able to treat up to 1,000 atoms quite routinely. So this is an example on a small peptide in water. So you have on the left graph the computational cost for the main 4 tasks that involved in such simulations. So this was done for the system that you see on the right, but increasing the size of the solvation shell. So that's why we have various sizes of the systems, which is given by the number of orbitals. And you can see that what is quite remarkable first is the calculation of the Kohn-Sham potential in red. You see that it is something which has very good scaling and which is really well under control. This is all PBE exchange correlation functional. So quite good scaling, quite good basis set, so it's accurate. The population analysis also are quite well, not so expensive. What is the most computationally costly is the calculation of the exponential of the Hamiltonian matrix in blue, which is imposing a rather bad scaling. However, thanks to the ScalaPack library, which is used to do that, you can see on the right that we still have good performances and good scaling up to a few hundreds of cores. So it's quite well balanced, but of course the story is not finished, and so we are now working on further increasing the efficiency of the code. So we are for the moment migrating the implementation to GPUs for the matrix exponentiation, and we still have room to improve a lot of the performances, by working on the parallelization. I think it could be doable. It should be doable with Daemon2K with this auxiliary DFT framework to treat up to hopefully 15,000 to 20,000 atoms within the next few years. So I think the auxiliary DFT is a good basis to work. So we then coupled this auxiliary DFT to QMMM to be able to treat large molecular systems. So these are the various schemes that have been proposed in the literature to couple DFT or real-time DFT to QMMM. The particularity of our scheme is to use a polarizable molecular mechanics force field. So we wish to be able to handle systems like the one represented in the center with a QM region treated by DFT and the surrounding treated by molecular force field. In our case, we wish to use a polarizable force field to take into account the instantaneous polarization of the environment by the electron dynamics, the electron density in the QM region, and vice versa. So to do that, we introduce an induced dipole on every MM atom that is calculated from the polarizability of the atom and the electric field felt by every atom. So we made various tests and showed that this simple point charge dipole model was a good model. And so the induced dipole further influenced the electron dynamics propagation by including the potential created by the induced dipole into the Kohn-Sham potential. We have further introduced the time delay involved in the propagation of the electric field that mediates the interaction between the electron cloud and the polarizable atoms, and on the other hand, the time taken to polarize the electron cloud by the induced dipole. So this has been implemented in Demon recently. So we have validated the scheme for various applications. This is quite standard, but we had to do it for our system. So this is a comparison of a polarizable versus non-polarizable QMMM absorption spectra for a DNA base pair in a protein DNA complex. So you see that the polarization of the environment can have an influence on the electronic spectra, and so it is important to take that into account. On the other hand, we also investigated the dynamics of the electron cloud as a function of the introduction of the polarization in the environment. So we took the same system and threw a proton, a 1 mega electron volt proton into the system. So this is the part you have on the right. So it's a small DNA protein complex. This is a QM region. And so what you have here are the evolution of the charges of the various DNA fragments by color as a function of time. So you see that around 1 femtosecond, you have the collision of the molecule with the proton, and that induce a lot of fluctuations in the electron density. So the the plain lines are the non-polarizable QMMM simulations, and the dashed line are the polarizable simulations. So you see that on the very short time scale during the irradiation, both types of curves are superimposed. So the electrostatic embedding doesn't really influence the ionization mechanism itself. It's only after a few femtoseconds, if you look at the zoom, that you start to have some variations between the polarizable and non-polarizable simulations. But these differences are rather small to my point of view, and probably the polarizable embedding scheme is not mandatory at this time scale of radiation chemistry. Might, I think, have more importance in the future. I think I just have a few more minutes, right?
You can have 5 more minutes.
Okay, so I will go. Okay, thank you. I was not sure about the time it started. Thanks. So I will finish with one application of these simulation tools to radiation chemistry problems. And I will give you the example of this pulse radiolysis experiment that was done by our colleagues Mehran Mostafavi at Orsay, who did pulse radiolysis experiment of this molecule in water in condensed phase in solution. And what they are doing, it's a kind of, we would say, a pump probe experiment, except that they don't use lasers, but they use beams of electrons to induce radiolysis. And they start to record absorption spectra 5 femtoseconds after the pulse, picoseconds, sorry, after the pulse. And what they saw immediately after the pulse is something a little bit strange. Usually, this type of irradiation is not really chemically selective because it's so energetic that you ionize, in this case, the 3 subfragments of the systems proportionally to the number of electrons they contain. So if you count, you would expect 1/3 of ionization on the base of the sugar or of the phosphate, more or less equivalently. But in fact, what they recorded was only a signature of the ionized phosphate a few picoseconds after the pulse. So it means that in these systems, when the base is irradiated, there should be a very fast sub-picosecond charge transfer between probably the phosphate and the base. But they couldn't really resolve the mechanism. So this is why we started to think about what theory and simulations could bring into that. So we first investigated if a charge migration mechanism could explain a charge transfer from the phosphate to the ionized base. So this is a computational setup. As I told you, it's a QMMM simulation. And what I show you here are two kinds of irradiation of the nucleobase, perpendicular or longitudinal to the plane. You have on the upper graph the evolution of the charges for the three fragments, U, P, and the water layer, and also the sugar. So you have a very fast, this is typical of the irradiation at the beginning. So you have a first perturbation of the density when the projectile, which is charged, is approaching, and then an ultra-fast ionization within a few hundred of attoseconds that lead to the ionization of the base. And within then the next femtoseconds, you see that the charge is going down, while the charge of the sugar is going up. So in fact, we have immediately after the pulse, in the next femtosecond, we have a delocalization between the sugar and the base, which overall has a rather steady charge. The electrons that were emitted are localized on the water layer that now have, by difference with the ground state, a negative charge. But you see that the phosphate doesn't have any positive charge. So this was obtained either with perpendicular collision. This is the same with the longitudinal collision. We also did simulations where we simulated irradiation by classical electrons, and we get the same picture. So we couldn't explain really the charge transfer from the phosphate to the sugar and to the base by charge migration. But we saw that in fact, by charge migration, the plus that is initially localized on the base delocalized also on the sugar. We then looked to another kind of chemical reaction that take place on a longer time scale, but could explain the experimental observation, is a standard Marcus-Serre electron transfer. So this is again a curve extracted from our simulation approaches. And so we evaluated the rate, and we found rates within a few tens of picoseconds. Finally, we could understand the ultra-fast sub-picosecond charge transfer by a non-adiabatic decay, because in fact, when we ionize the molecule, most of the time we end up in this part of the potential energy surface, and upon relaxation, this U plus SP potential energy surface crosses the other potential energy surface with a charge transfer to the phosphate, from the phosphate. And the electronic coupling is rather strong. And so this is what we think is taking place in the experimental. So I will conclude now with some just remarks. So I showed you a few applications and of the auxiliary DFT framework to problems of radiation chemistry. So for us, it is really a beginning of a long adventure, if I can say. So we still have a lot of things to do on the methodology. There are various things that I haven't spoken about today, like the dynamics of secondary electrons, nuclear quantum effects, also a lot of things about the basis set that we are really wondering about. And we have various applications going on with our colleagues in Orsay, and also, including biophysics physicists, and also people in Toulouse working in interstellar chemistry. So, and finally, I would like to just mention that we are looking quite actively for young researchers who would like to apply for CNRS position in our lab, so for the next year. So if you are interested, please don't hesitate to come and discuss with us. We have quite a broad area of expertise, both for development of DFT, but also for application. So we would be happy to discuss if you are interested. And I will conclude simply by acknowledging all the people who did the work, and especially this branch of 5 people from Xiaoqing to Karim, who really did most of the work that I showed today. So I would like to thank them a lot. My collaborators in Orsay and in Paris, on the left, and also all the collaborators from Demand 2K, with who we have a lot of interactions quite regularly. And I will finally thank you for your attention, and I'm of course open to any question that you would have.
Thank you very much, Leo, for this very interesting talk. It's really nice to see how under the umbrella of attochemistry we can have problems like we saw this morning from small body atom set up until biological sized molecules. Okay, are there any questions? So please raise your hand. If not, there's already a very short question in the chat by, let's see, Marcus Dahlstüder, it's abbreviated, by Marcus. He just says diabetic equals to non-adiabatic question mark. I'm not sure to what it was related. Maybe, Marcus, you can elaborate a bit more on this, if you're still here.
No, it's just about the semantics here in the field. So is non-adiabatic the same thing as diabetic in your presentation?
Are you referring to the kind of to the kind of exchange correlation potential we are using? Or are you talking, for example, of non-adiabatic coupling in electron nuclear?
Yeah, I guess the latter. Yeah.
Okay. Yeah. So for the moment, what I showed anyway today was what we call purely real-time TDDFT. So nuclei are not moving at all. So for the moment, we have started to introduce electron nuclear non-adiabatic coupling via the ARN-FEST MD simulation. So the code is implemented. We are testing it for the moment, but we haven't really used it in any applications so far. I don't know if this answers your questions.
Yeah, thank you.
All right, are there any more questions? Yes, I see a raised hand by Gilbert. Please unmute yourself and ask.
Yeah, hello. Thank you for
Hello.
the nice talk. I have a question. So I'm a bit familiar with this topic of radiation damage. And when we do the simulations, we had this nice picture where like a particle was trespassing through basically the DNA and ionizing like substructures of the molecule all along its pathway. And as you said, what happens is that you ignite all kinds of nuclear dynamics, ionization processes. You have secondary electrons, and each of these secondary electrons on its own also starts a new cascade of processes. And you mentioned briefly that you, in principle, are able also to trace probably these secondary electrons and the involving effects. And I just was wondering, since you claim that you can do a couple of thousand atoms, and with these simulations, how far are you with tracing all the secondary processes? Do you impose certain cutoffs of like depth layers in the cascades that you can trace, or how you are doing that?
That's well, you are familiar with this topic, so yeah, I think that's a really interesting and for the moment still unanswered question, where the secondary electrons are going and what they are doing in the surrounding. As far as I know, I think it's not well known experimentally what is the kinetic energy of these electrons in condensed phase. So for the moment, the problem we have some ideas to work on that. For the moment, we have the problem of the fact that electrons are I will have difficulties to say that in English, that you cannot distinguish electrons. And so of course you have only the quantum density. So we are working with my colleagues Julien Pilmet, who is working in Paris, to see if we can develop descriptors that would really allow us to track indirectly the secondary electrons. So this is something on which we are only starting to work. So far, we only indirectly said that secondary electrons are localized where charge is accumulating during the dynamics with respect to the ground state. But this is only an approximation. In fact, we don't really track secondary electrons. And there is also all the problem of electronic decoherence, which is completely absent from the scheme that I showed you today, that that has for consequences that we cannot, to my point of view, with the schemes that we are using, the standard real-time TDD-FT, I think we cannot, without introducing decoherence, we cannot simulate the irradiation and the attachment caused by secondary electrons that we produce directly by ionization, because they are scattered over all directions. And so finally, they are diluted in the surroundings. So we are only at the beginning of that. So I hope I was not too claiming that we were doing too much things. We are working simply on that. So I would be happy to discuss with you about if you have any ideas.
No, I don't think that I can help you there. but no, I was just very, when you said that, I was just very curious how you are going to do that. Okay. Thank you.
You're welcome.
Okay, very nice. So if there are any other further questions, I would ask you to postpone them to the Meet the Speaker session after the first talk. And I would like to thank Oriol again for his very interesting talk. And we would now move on to our second speaker of this afternoon, with is Felipe Zapata from the Department of Physics at Lund University in Sweden. And they will talk about implementation and validation of the relativistic attosecond transient absorption theory within the dipole approximation. So Felipe, please share it.
Okay, I'm going to share the screen. Yeah. Can you see moving the slides?
All is good, all is good, perfect.
Okay, so here. Okay, so thanks a lot and good afternoon. First of all, thanks for the organizers of Attochem for making possible these conferences in these difficult times. These virtual meetings help us a lot. I think at least help me a lot to keep alive the passion of what we are doing every day. And also thanks Ladislao for all the technical support. So I'm Felipe Zapata, currently working as a postdoc fellow, as you said, at Lund University in the group of Jan Marcus Dahlström. And the work I'm going to present today has been recently published and is a result of a strong collaboration with the group of Eva Lindroth at Stockholm University. So before I started my job in Marcus' team, Jimmy and Eva, they developed a many-body relativistic code where the source orbitals were computed at the Dirac-Fock level. So my work consisted to extend this code to the time domain in order to explore the electron dynamics under the influence of a time-dependent electric field. So the time-dependent extension of the code allowed us to develop the relativistic attosecond transient absorption theory that I'm going to present to you today. So, as you know, attosecond transient absorption spectroscopy is used to study electron coherence and motion in atoms and in molecules. Typically, an intense laser field is used to prepare an electron wave package in a specific state or in a coherent superposition of states, while an XUV pulse is used to probe the dynamics. And in transient absorption spectroscopy, the target quantity is the exchange energy between the total electric field and the atom. And we call this quantity delta epsilon. You can easily find general reviews on experimental and theoretical transient absorption theory. Here I give you some of the most famous, but all the studies so far are based on non-relativistic transient absorption theory. So regarding the lack of a relativistic transient absorption theory that can handle strong fields far beyond the perturbative regime, we decide to derive a relativistic ATS theory based on the time-dependent Dirac equation within the dipole approximation. So for the moment, in our development is restricted to the single particle interpretation of the Dirac equation. So in my talk, I'm going to first introduce you the relativistic transient absorption theory. Second, I will show the numerical simulations we have carried out in order to validate our equations. And finally, I will show you the extension of this relativistic transient absorption theory that we have validated in one electron atoms to the case of many electron atoms. So let's start. So thanks to the conservation principle, the exchange energy between the laser and the atom can be calculated as the energy absorbed by the atom from the electric field. Then the total energy absorbed is given by the integral of the instantaneous power running for all times. And the instantaneous power is defined as the time derivative of the time-dependent expectation value of the energy of the Hamiltonian of our system. So basically, the instantaneous power shows us how the energy changes with time. And thanks to the Ehrenfest theorem, we can compute this instantaneous power as you can see here, where the dot over the time-dependent Hamiltonians mean the time derivative, and C of t is the electron wave function. So as it is known, in presence of an external electric field, this quantity, the instantaneous power, is not gauge invariant. That means that the total Hamiltonian is not anymore a constant of motion. This fact will imply that we have a redefinition of the energy scale at each time step. And this question is an old question and is addressed in many textbooks, and also a gauge invariant formulation of these quantum mechanical problems was formulated by Young in the 70s, and later also co-proposed also another gauge invariant formulation, but using the Dirac equation. For the moment, we have not implemented any of these formulations, but in order to eliminate the gauge ambiguity, we decide to introduce a new quantity, what we call the relative instantaneous power. And this relative instantaneous power is defined as the difference between the atomic instantaneous power and the instantaneous power of a free electron subjected to the same time-dependent electric field. So in this way, the free electron system serves as a physical reference for the energy and for the power. And as I'm going to show you, this subtraction that we are doing is going to correct the time-dependent power without affecting the total energy gain. So the derivation of the relativistic instantaneous power begins then with the time-dependent Dirac equation, where the time-dependent Dirac Hamiltonian is divided into the field-free Dirac Hamiltonian and the interaction term. Here you can see the field-free Dirac Hamiltonian, where basically these two first terms correspond to the relativistic kinetic energy of the electron, And the interaction with the nucleus is described here with the Coulomb interaction. And then the alpha matrix is basically composed by the Pauli matrices. And the beta matrix is given here. So within the dipole approximation, the time-dependent interaction term can be expressed in the length form, where Z means is the electron position, E of t is the electric field, and little e is the electron charge. So after the derivation of the expectation value of the time-dependent Hamiltonian, we can obtain the energy gain by the atom, which is given by this expression. Okay, and by doing the Fourier transform, we are going to obtain the Fourier, the frequency resolved energy gain spectrum. So this quantity, which is going to be gauge invariant, because at the end of the interaction with the laser pulse, this energy gain is going to be gauge invariant. So the frequency resolved spectrum is, of course, gauge invariant. Where here Z of t is the expectation value of the dipole, is the dipole, the time-dependent dipole. E dot E is the derivative of the electric field, and then so what we have here is going to be the Fourier transform of the dipole and the Fourier transform of the total electric field. And this expression is the same that we can find in the non-relativistic attosecond transient absorption theory. So the second possibility is that we can use within the dipole approximation is to use the velocity form. In this velocity form, now the interaction term is given by the alpha, the Z component of the alpha matrix times the vector potential. So again, by derivation, we can obtain the energy gained by the atom. And by doing its Fourier transform, we obtain the frequency resolved energy spectrum. And now here, the expression of the energy gained by the atom, this we can see very easily here in the velocity form that it in fact corresponds to the classical work. Here inside the integral, what we have is the power. And we can interpret the product of C times the alpha, the Z components of alpha as the velocity, as the electron velocity. And E is going to be the force. So we are going to have here the power, and the integration will give us the work that we are introducing into the system. And again, here in the frequency resolved spectrum, we will need the Fourier transform of the alpha, of the Z component of alpha, and the Fourier transform of the vector potential. So now the question is, after deriving these expressions for the length and for the velocity gauge, the important question is to know the limits of this expression, if they are valid for all perturbation regimes. So normally the limits will be defined by the domain of the physical phenomena that we want to explore within our theory. So the range of applicability is going to be controlled, but mostly by two parameters. First of all, the atomic nuclear charge, and the second parameter is the strength of the laser field that we are going to use to irradiate the system. So from a very general point of view, you can see here this representation. So the horizontal black line will represent together the nuclear charge and the strength of the laser field. So in one side of this representation, we will have what we call the non-relativistic limit of the theory. Here, in this limit, the atoms has a very low nuclear charge, and the laser is soft, have a soft strength. It's a soft laser field, we can say. And then we have all this region up to this vertical black line, where the single particle interpretation of the Dirac equation is valid. Beyond this this solid black line, we are so beyond the single particle interpretation, and then per creation process has to be considered. So we are really in these relativistic many body processes. Here we are really with very high effective charges. So, for example, in nuclear collision experiments, or using really strong laser fields that can polarize the vacuum. But for the moment, we are not interested in this region. So we are interested in the region of the single particle interpretation. And also, on top of that, we are within the dipole approximation. So we have to stay up here, no, to the left of this dashed red line, where if we pass this line, we will need to introduce beyond dipole effects into the description of the interaction with the laser field. So within this simple picture, it is the first step for validate our theory will be to compare, or to think that okay, if is our theory able to describe the non-relativistic limit. So this is like the first step, and this will allow us to compare our results with the well-established non-relativistic calculations using the time-dependent Schrodinger equation. So this is the first step in the validation of our theory, to understand if we can reproduce with our equations the spectrum in this region. So in order to validate our theory, so we decide to carry out different calculations on the hydrogen atom, which is a very low relativistic atom. And we're using two different scenarios. So the first is a very simple single photoionization process. And the second one is a multiphoton ionization process through a resonant state. We want to be able, with our method, we can describe also multiphoton ionization processes. So here in this first figure, you can see the expectation values computed with both the relativistic and the non-relativistic code that we have also in our group. And you can see the dipole, the electron position, and the velocity of the electron. And you can see that they overlap, the relativistic and the non-relativistic calculations. And the error, the difference between, not the error, sorry, the difference between the both calculations are in fact found in the error introduced by the propagator that we use to propagate the equations. So we can say that basically, from a numerical point of view, both calculations are identical. In these two figures here, you can see in the panel, in the left panel, you can see the power transferred to the atom. Again, computed with the Schrodinger equation, with the time-dependent Schrodinger equation, and with the time-dependent Dirac equation, and in both, in length and in velocity. We see that the length of that they overlap, the calculations, but what we can see here is that this quantity is, as I told you, is not gauge invariant. So we see that they don't, it's a different quantity when the laser field is on, so they are completely, the oscillation, they don't overlap. And here in the right panel, what you can see is the energy gain by the atom. Again, here you can see that in presence of the electric field, the two quantities are not gauge invariant, but after the end of the laser field, when it's turned off, this quantity is gauge invariant. So the total energy gained by the atom is the same, described by the length or the velocity forms. So in order to remove this gauge ambiguity, I can show you now the relative power and the relative energy gain. So by subtraction of the power of the free electron motion. So we can see that now the power, the huge oscillations are decreased. So, but still the curves don't overlap. Okay, so they are still, this quantity is still is not gauge invariant. But at least we can understand that these huge oscillations that we can see here, they are coming from the contribution of the free electron moving in the continuum. And what we can see here in the right panel is the energy gain, and the same. We see that it's not gauge invariant while the laser field is on, and then at the end is gauge invariant. So now what we can do is to do the Fourier transform of this signal to obtain the frequency resolved spectrum, which is going to be a gauge invariant. And here you can see the spectrum calculated for the 4 different calculations with the non-relativistic and the relativistic. And also you can see here I put the Fourier transform of the electric field. So you can see that we have an absorption peak at the frequency of the electric field that we are using. Then I will show you now directly the frequency resolved spectrum for the multiphoton ionization process. We are using a 2-photon pump and then a probe. That from the 4s state, we go to the continuum. And in the spectrum, we can see the 2 peaks corresponding to the pump and to the probe. And we see that our relativistic code is able to reproduce this non-relativistic limit. So now we are not going to stay here. We want to go to more interesting systems. So we have what we want to explore now is heavy atoms like the krypton or xenon, but still within the dipole approximation. So it's like we pass this line, this purple dashed line, and we will find in this region here now, where some relativistic effects, such as the spin-orbit coupling, is a very important effect when describing processes in krypton or in xenon. So in order to describe the electron dynamics of these many electron systems, we decide to develop a relativistic time-dependent TDCIS method. This relativistic TDCIS method is based in the same philosophy of the non-relativistic TDCIS method developed in the group of Robin Santra, for example. So basically, this method, the time-dependent wave function, is expanded onto the single excited states. And these single excited states are built up using the Dirac-Fock orbitals that we obtain by solving the Dirac-Fock problem. And of course, the Dirac-Fock orbitals are 4-component spinors with the large and the small component, and where the angular part is going to be controlled by the quantum number kappa, with kappa, as you know, relates the L and the G quantum numbers. So I present you the equation of motions that we have to solve. This is for the ground state, the coefficient of the ground state, and this is for the equation of motion for the excited states. In order to solve these equations, we have implemented some approximations to reduce the computational time. So, for example, one of the important approximation is, as we are not interested in the pair creation process, so we have removed from our basis the orbitals corresponding to the negative energy states. So by doing this, we are forced to use in the time propagation the length gauge. And this question has been addressed before by Alejandro and Eva Lindroff also, that we can see that when removing the negative energy states, the best option is to do the propagation in the length gauge.
And also 2 more minutes.
Thank you. And then we have also introduced a complex absorbing potential to avoid reflection and to reduce the simulation box. So finally, just to finish, here I show you the preliminary results for the krypton atom. In the right table, you can see the energies for few single excited configurations. And in the left, you have for the same configurations, all the states that we have when we solve the relativistic problem. So this is thanks because the spin orbit effect is embedded in our theory. So here with this method, it is not necessary to introduce ad hoc the spin orbit coupling. We have this already. So you can see here a comparison between NIST and our calculations. And here I give you the B-spline parameters that we are using in our relativistic and the non-relativistic code. And here is just a transition using the relativistic and the non-relativistic code. And as you can see, well, with the relativistic code, we are able now to create coherent superpositions of more state that contain the spin orbit coupling. So there is still a lot of open questions and things that we would like to do. For example, to maybe develop a theory within the gauge invariant formalism. Also, we would like to go beyond the single particle interpretation, and why not to study the positron-electron pair creation using transient absorption. And this is in fact in the line of this article from written by Alfred Maquet and Rainer Groth about this possibility of exploring positron-electron pair creation or relativistic effects with the tools that we know and the methods from attosecond physics. And now we are, finishing the extension to the many electron atoms. So thanks for your attention.
Thank you, Felipe, for this very nice talk about a very in-depth description of atomic systems. Do we have any questions? Maybe let me have a look. Do we have any raised hands? As far as I see, there are no questions at the moment. So maybe let me ask just briefly before we go to the next speaker. You compared to non-relativistic TDHE in your calculations and then for the hydrogen, but also I saw later for the heavier atoms. Do you have anything on the timings, like how much computational more demanding your approach is?
The time propagation scheme is not is in the same order of time. It's not so much. The consuming part is to create all the bases and to compute all the matrix elements. Of course, we are using polarized laser fields, so we are reducing the angular momentum, so it's reduced. So we are m is equal to 0. So we are not, for the moment, we are not considering polarized laser fields or no. So it's conserved. The m quantum number is conserved. So this reduces a lot the simulation time.
Okay, thank you very much. Then thank you again for the talk, and we will go to our third speaker of the session, which is Thierry Tran from Department of Chemistry, UCL, and also Imperial College London, the UK. And he will talk about control of electronuclear dynamics with IR pulse, simulation with quantum Ehrenfest. So Thierry,
Yes, can you hear me first?
Yes, I can hear you, and you can share your screen. You can start.
Perfect. Well, first, thank you very much for the introduction, and also I would like to thank the organizer for the opportunity to present my work in this workshop. So, well, as the chair frankly introduced, we'll talk about control of electronuclear dynamics with the aim of an infrared pulse and the method I will be using, the quantum Ehrenfest. So a bit of an introduction first. So thanks to the recent advance in attosecond technology, now we have better time resolution on spectra, so we can finally be able to monitor electron dynamics and its effect of the electron dynamics on the nuclear dynamics, and also allow us to unravel the mechanism behind ultra-fast phenomena. So in a standard attosecond spectroscopy experiment, there is two pulses involved in the experiment. The first pulse is the pump pulse, which comes from either a high harmonic generation source or a free electron laser. And the energy of this pulse can range from the XUV to soft X-ray, and energy for this photon usually end up photoionizing the system. And because of the fact that we have quite a small, a very short time pulse, it means that we have a not so well-defined pulse in the energy range, so quite a broad pulse in terms of energy range. So usually we hit multiple electronic states at the same time. So we end up creating a coherent superposition of state, in that case of the cationic state. And then, as for the second pulse, the probe or control pulse, the nature of the pulse may differ based on what kind of things the experimentalists are looking for, either to control the dynamics, or, for example, doing coionization in order to probe the electron dynamics itself. So the goal of my project was is to simulate the dynamics of molecule upon photoionization, photoexcitation, using the sudden approximation. So we don't include the pump pulse in the dynamics. We just assume that we start with initial state on the superposition of cationic state, and we want to investigate the effect of that electronic currents on the dynamics, and also being able to control the electron and nuclear dynamics using a subsequent control pulse, and ultimately being able to reproduce predict spectroscopy results. So the thing is that for that kind of simulation, there is many challenges. I mean, first of all, is a problem of the dimensionality. We have multiple electronic states, many degrees of freedom. So if we have to do the full simulation in its full dimensionality, it can be quite expensive itself. So we have to find a balance between the accuracy of the representation of the electronic and nuclear wave function and the time it takes us to run the simulation. So here on that slide, I'm just showing a short review of an available method for non-adiabatic dynamics that you can find in the literature, at least the most common one. The speaker from this morning have already touched upon the topic of a method such as AIMS, which stand for ab initio multiple spawning, or MCTDH method. So I will just do a quick review on them. So you have a surface hopping method or RNFS method that is quite popular in the literature, where you represent the nuclear wave function with non-interacting classical trajectories that propagate on potential energy surface that is often computed on the fly. Then you have the Ames method, where you have also classical trajectory, but they have the trajectory are interacting with each other because you expand the nuclear wave function into a basis of Gaussian wave packet. And then the methods I'm using for my work, which is DDVMCG and one of its subsets, the quantum RNFS, where we also have the nuclear wave function, which is expanded into basis function, but on top of that, we have quantum trajectory. So I will mention later what I mean by quantum trajectory. So in the DDVMCG method, we are trying to have a full quantum treatment of both the electron and nuclei with ab initio method. And for that, we solve the time-dependent Schrodinger equation for both the electron and nuclei using a variational solution. And similar to other methods like Ames or surface hopping, most of the time the potential energy surface is computed on the fly. And so the thing is that so in DDVMCG, the nuclear wave function is expanded similar to Ames in a linear combination of Gaussian wave packet, where you have the expansion coefficient A, the Gaussian wave packet themselves G. And inside of the Gaussian wave packet, you have different parameters such as the width, alpha, the center of the position of the Gaussian wave packet, the momentum, and its phase. And the equation of motion for DDVMCG are derived by solving the time-dependent Schrodinger equation by using the Dirac-Frenkel variational principle, which is just shown here, which allows us basically to always guarantee that we have the optimal time evolution of our nuclear wave function, and thus we end up having what we call the quantum trajectory for the when we integrate the equation of motion. So on that slide, you can see the equation of motion that we have for DDVMCG. So first we have the equation of motion for the expansion coefficient that involve overlap matrix, the Hamiltonian, the time-dependent overlap matrix. And then we also have the equation of motion for the Gaussian parameter. So inside of the character here, it's entered all of the Gaussian parameter, the width, the momentum, and the propagation. Also, the thing is that in DDVMCG method, we use frozen with Gaussian wave packet. So the width of the Gaussian wave packet doesn't change with respect to time. So the only things that evolve in that case would be the phase, the center of the position, and the momentum of each of the individual Gaussian wave function. And in DVMCG, the equation of motion involves this so-called C matrix that you have the form below that involve again some overlap matrix, derivative of the overlap matrix, as well as the nuclear Hamiltonian matrix. And the thing is that in DDVMCG, one thing we have to compute, so the potential energy surface is computed on the fly, and one of the approximation we do, because we evaluate only the quantity at the center of the Gaussian wave packet, but in order to properly do the interaction between the different Gaussian wave packet, we do the so-called local harmonic approximation. So we expand each of the potential energy surface around each of the Gaussian wave packet by computing the gradient and the second derivative. So now I will just do a few mentions about the quantum RNFS method. So the quantum RNFS method is based on the DDVMCG frame. So the nuclear dynamics is propagated in the exact same fashion with the exact same equation of motion. The difference is that in quantum RNFS, instead of having multiple potential energy surface, we each Gaussian wave packet see only one potential energy surface. And the derivation for the method can be started from the exact factorization itself. And because we only have one potential energy surface, it means that we have a time-dependent electronic wave function that is that can be itself expanded into a linear combination of diabatic state. And the equation of motion for the electronic wave function is shown here, involving the electronic Hamiltonian and the coefficient of each of the diabatic state. And what is particular with the quantum interference method is that the electronic wave function is propagated directly within the electronic structure code. So the advantage of a quantum interference is that since the electronic wave function is propagated directly within the electronic structure method, we don't need to compute all of the potential energy surface explicitly with the gradient and second derivative. We compute only one potential energy surface that is a linear combination of all of the states with their respective population, electronic population, and we only have to compute one gradient and one second derivative for each of the Gaussian wave packet. So now I will just go on to the electronic structure method. So for my work, the main method I'm using is a complete active space self-consistent field. So the way it works, KCCF, is pretty straightforward, is that you define an active space where you put some orbitals that you call active orbital, and you just generate all the electronic configuration state function within that subset of active orbital. So with that method, we capture the static correlation. The challenge is the dynamic correlation. You can capture the dynamic correlation by expanding the active space using KCCF directly, or if you want to reduce the cost of the computation, you can use a restricted active space, which is a subset of the KCCF method, or you can use a perturbative approach like CASPT2. So in order to simulate the effect of the pulse within the dynamics, so the control pulse in our dynamics, we have implemented the effect of the oscillating electric field directly within the electronic structure method by including the dipole electric integral within the one electron Hamiltonian. So the effect of the pulse is only treated within the electronic structure method. So the electronic wave function will feel the presence of the pulse, and we do the integration of the equation of motion directly within the electronic structure method to include that pulse. And the form of the pulse is a Gaussian shape, standard Gaussian shape pulse that is shown here. So I will show now on the next, for the rest of my talk, I will show some results on the investigation we have done on the control of the dynamics on Aline and Ethane. So first we start with Aline, that we have used it as a two-state model system. So the aim of that work was to see how we can control electron and nuclear dynamics with the help of an infrared pulse. And you can see on the right-hand side, basically the shape of the pulse. So it was quite large pulse compared to a standard attosecond pulse. So we have quite a few number of cycles within our pulse. So in a case of a two-state system, the general solution for the time-dependent Schrodinger equation, if we have to solve it by hand, will obtain the following solution for the electronic wave function, where you have state 1 and state 2, where they associate in time respect to the energy of the state. And if you were to compute the density of the electronic wave function, you will get that following equation. And you see that if we look at the important terms that that shows the time evolution of the two populations, so basically the oscillation between the two states, we see that the oscillation between the two states depend on the energy difference between the states. So the smaller the energy difference is, the longer is the oscillation, so the electron dynamics oscillation. And so if we reach a conical intersection where basically the two states are degenerate, we expect to see a collapse of the electron dynamics. So basically you will see during the time when it's going through the conical intersection, it will be a kind of a flat line. And when we do the dynamics itself, so the thing is that without here we do a comparison of the dynamics of Aline with the contour phase method with and without the pulse. Also, something I forgot to mention is that the pulse, we have aligned it in the Z direction, which is basically along the direction of the molecular axis of the molecule. And we see from that dynamics, given the initial condition we have, we go through a conical intersection at roughly between 10 to 15 femtoseconds. So we see this collapse of the electron dynamics in the spin density. And if we look at the adiabatic population of the cationic state, when we compare the no pulse and the pulse, we see, first of all, a quite large effect of the pulse on the adiabatic population itself. And as a consequence of it is that if we monitor the spin density, so the spin density basically allows us to monitor where the hole is located on the molecule. In that case, here we do the spin density on one of the carbon atoms on one end of the molecule. And then so we see this nice electron dynamics oscillating, and then as soon as it reaches the conical intersection, we see that there is a collapse of the electron dynamics, and the pulse affect how it goes through the conical intersection. And and by looking at the effect of this electron dynamics on the nuclear dynamics, we see the oscillation of the two CC bond length. And when we put the pulse in the dynamics, we see that the spin end up at some point locating on one end of the molecule, and as a result of this, we see that one of the bond length is getting more stretched than the other. So we are getting asymmetry in the molecule. So we are converting into an asymmetric stretch of the molecule. So now I will move on to the Ethane work that we have done, that is currently ongoing work. So again, it's a similar goal. We want to investigate the effect of the electronic currents and the initial electronic superposition. So what is this electron dynamics and its effect on the nuclear dynamics, and as well as what happens when we include the pulse in the dynamics? How do we affect this electron dynamics and nuclear dynamics? And this work is based on the already previous experimental work where they have photoionized molecule. So they're using a pump pulse that come from HHG source. And using the photoionization cross-section, they managed to determine what was the relative weight between the different cationic state based on the different harmonics they use to photoionize the molecule. And one of the main results they observe is, of course, different nuclear dynamics, and its direct effect is that they have a different fragmentation pattern based on the HHG pulse they use to photoionize the molecule. And one of the subsequent work they have done is that they have included a control infrared pulse in the dynamics, and they managed to change the fragmentation pattern of ethylene using this infrared pulse based on the time delay of the pulse itself. So ethylene is a rather small system and also a highly symmetric system. And usually when we treat non-adiabatic dynamics involving conical intersection, we often like to use symmetry rule in order to determine what is the degrees of freedom that span the different conical intersection. So we can easily rationalize based on the symmetry of the state what will be the degrees of freedom that will lead you to the decay through a conical intersection, and what is the mode that lift the degeneracy between the state. And the thing is that this argumentation can be also used for dynamics outside of conical intersection when you generate a superposition of state that doesn't have to be close in energy or even degenerate in energy. And so in order to for that symmetry rule, what you have is that you need that this irreducible representation of the electronic state 1, electronic state 2 times the irreducible representation of the normal mode of a certain symmetry should give you the totally symmetric mode. And this is a symmetry rule we use for chemical intersection, and we can apply it for general dynamics, as I say, for a superposition of state. And we were trying to investigate the dynamics of ethylene by looking at by pairwise, by pair of state. See if we can rationalize the complicated dynamics where you have where they have photoionized the system to multiple state by dynamics of a subsequent pair of state. So on that slide, it's a summary of basically what we obtain when we do the symmetry product for the ethylene cation. So on the left-hand side, you have the symmetry label of the different cationic state in the D to H point group. And the right-hand side, you have the normal mode motion as well as the symmetry label. And for example, if we have to treat a superposition of state for the D0 and D1 state, the normal mode that lead to the conic intersection is torsional motion. And for other state, for example, the D1, D3, the motions that lead to the conic intersection would be normal mode 9 and normal mode 7. So in the mass experiment, what they have observed, the main photo product was the fragmentation, so the loss of one hydrogen or two hydrogen. So in our dynamics, we analyze mostly the dynamic by looking first at the torsional motion and the normal mode 9 to 12, which correspond to the 4CH vibration. So on that slide here, you can see the result for the dynamics where we have initiated our ethylene cation on a superposition of a 50-50 D0 D1 state, with and without a pulse. So the pulse, we have put it in the y direction, which correspond again along the molecular axis. And we can see that on the adiabatic population, with and without the presence of the pulse, we don't see large effects from the presence of the pulse itself, but onto the nuclear dynamics, we see quite a consequential effect from the pulse. I mean, first of all, from the symmetry rules, we have determined that in the superposition of a D1 D0 state, the main leading motion will be the torsional motion, which is shown here in red. And we see that initially our nuclear wave function is totally symmetric. So due to the symmetry of the wave function, we shouldn't have any gradient in any direction that breaks the symmetry of the wave function except the totally symmetric mode. And normal mode 10 is one of these totally symmetric mode. And we see that the first mode that show asymmetry is a normal mode 4, which is what we expected from the derivation from the symmetry rules. And as soon as we move along the torsional mode, we lower the symmetry of the molecule, so it's no longer a D2H symmetry point group. It becomes a lower point group, which is in that case a C1, and thus other motion becomes symmetry or low in that new point group. And due to the character of the state, one of the normal mode we expect to see the gradient appears is along normal mode 11. And we can clearly see that normal mode 11 here in purple is picking up as soon as normal mode 4 has broken the symmetry of our nuclear wave function. And if we have to represent the dynamics in a different way, for example, by using the whole locations on the left-hand side, what we have plotted is the configuration state function linked to the orbital on each of the 4CH bond to see where the charge is located on our molecule. And in the case of the no-pulse dynamics, we can see quite a chaotic oscillation of the charge between both ends of the molecule. And as soon as we put the pulse in the y direction, we end up creating an asymmetry of the charge oscillation, and we end up seeing it located on one specific end of the molecule. So it would be CH2. Well, this one is CH3, so CH2 and CH5. So we end up on one specific, on two specific CH bond. And if we translate it into the nuclear, the CH bond length, we see that in the case of the no pulse, we deposit energy into two bond lengths. So the thing is that in our dynamics we cannot simulate fragmentation itself, because it's a phenomenon that occurs much longer later down in the dynamics, often in the time scale between from nanoseconds to maybe a microseconds, whereas here the dynamics is done in the femtoseconds window. So we can only give a qualitative picture on where the energy is deposited. We cannot say what is a quantitative fragmentation ratio, but here we can basically say that we have energy deposited into two bond lengths, whereas as soon as we put the pulse first, we dampen the fragmentation effect, or at least the energy deposition, and we only deposit energy in one bond length in that case. So the main conclusion is that dynamics initialized on a specific superposition of state can be rationalized using symmetry rules. We get conical intersection like dynamics even outside of region of degeneracy. And we see that electronic currents play quite an important role on the initial motion of the nuclear wave function. And when we include the pulse in the dynamics, we induce different electron dynamics, and by consequence, we also get a different nuclear dynamics, and thus a different photoproduct. So I would like to thank Professor Graham Orff Group, as well as Professor Mike Rope, for the supervision and the help throughout this project. Thanks for your attention.
Thank you very much, Yeli, for this interesting talk. There are any questions? Please use the reaction or help you raise your hand button. I will have a look if there are any. Not so far, at least. Maybe I'll just start with a short question. So you were talking about that you need to include in your quantum chemical approach, you need to include dynamic correlation. You have the static with a complete active space, and you need to include dynamic, and you were giving some example, and for example, perturbation theory or something like CAS-PT2. And I was just wondering, because you then talk about conical intersections, how well does CAS-PT2 then still work? Like when you go into conical intersection region with intruder states, or problem that some perturbation gets too much weight in your calculations?
So I haven't run dynamics with CAS-PT2 myself. I know a bit from working with another colleague. So the thing is that for the CAS-PT2 method, you have different Hamiltonian. So you have the single state, multi-state, and extended multi-state CAS-PT2. And I know, for example, when you want to treat conical intersection more accurately, usually you tend to end up using extended multi-state CAS-PT2 for the kind of things. And there is also this IP shift that you can use in order to remove introduced state. But from there's one paper now, I can't remember the author, but where they were discussing about this IPEA shift that may be just a factor that you don't want to include because it's arbitrary correction that may not work all the time.
Okay, thank you very much. And we do have another question. Hubert Dordiol, please unmute yourself.
Yeah, I have a small, maybe more technical question, but I think it would be interesting to see that the advantage of this method is that it's dealing with one single state for each Gaussians, that is like similar to the Ehrenfest trajectories. And I was wondering, how do you express this electronic state? So you are using CAS-SCF, and you were saying that you need only one gradient for the electronic states to propagate it and evolve it. But then if you expand it on CAS-SCF states, I would expect that you have to calculate the gradient for each of the CAS-SCF states that are involved.
Yes.
Is it true?
So the thing is that this is the reason why I say that the particular flavor of our quantum manifest method is that the electronic propagation is done directly within the electronic structure method. So in the case of CAS-SCF, we have an active space where we end up, let's say, for example, having 120 configuration state functions, our RNFS state is written as a linear combination of this 120 configuration state function, and we propagate this coefficient in time. So we never compute explicitly the adiabatic or diabatic state itself. We compute only one state, which is the RNFS state, which is just in that case the solution of the time-dependent Schrodinger equation.
Okay, okay. And the gradient is just then calculated using these coefficients?
So the thing is that we also don't compute the adiabatic gradient. We compute the gradient for that specific RNFS state. So because of this, we end up, we don't use, when we compute the gradient and the second derivative using the CP-MCSCF, we don't solve it for the simplified CP-MCSCF. We use a full CP-MCSCF to solve the equation because we don't have eigenstate.
Okay. Okay. Thank you.
Okay, I do see that there are two more hands raised, but unfortunately we have to move on to give our fourth speaker enough time. I would ask you, Morgan and Alicia, to address your question in the Meet the Speaker session after the fourth talk to Tia directly. And yeah, thank you very much for your talk. And